When we think about a data center, we normally think about servers, switches, routers, storage, and maybe cooling systems. But there is something connecting all of them together: cabling. A modern data center can have thousands or even tens of thousands of physical connections, and one small cabling problem can take down a server connection, a switch uplink, or even an important network path. So, in this episode, we're going to look at the physical side of networking: copper, fiber connectors, transceivers, cable management, labeling, testing, and finally some real-world troubleshooting. So, what exactly do we mean by data center cabling? Simply put, it is the physical infrastructure that connects one equipment together. A server needs a connection to a switch. A leaf switch needs connections toward the spine switches. Storage systems need connectivity. Management networks need connectivity. All of those connections eventually depends on some type of cable. And generally we're dealing with two major technologies: copper and fiber optic cabling. Let's start with the basic difference between copper and fiber. Copper carries information using electrical signals. Fiber, on the other hand, carries information using light. Copper is very practical for many short distance connections, especially management interfaces and standard Ethernet connections. Fiber becomes extremely important when we need higher bandwidth, longer distances, and high-speed data center connectivity. So it's not really about saying one is always better than the other. It's about choosing the right medium for the connection. Fiber is interesting because we're no longer sending electrical signals through the cable. We're sending light. Imagine we have device A and device B. Device A transmits light through the fiber. Device B receives that light and converts the signal back into data. And communication works in both directions. This gives us two very important terms that you'll hear constantly when troubleshooting fiber: TX transmit and RX receive. We'll come back to these later because understanding TX and RX is extremely useful when a fiber link goes down. Not all fiber is the same. Two of the most common types are single-mode fiber and multimode fiber. Single-mode fiber is typically used when we need longer distance communication. You'll commonly see it used between buildings, sites, data center areas, or other longer optical paths. Multimode fiber is commonly used for shorter distances, such as connections within a data center. The important thing is that the fiber type must match the optical transceiver and the design of the link. You cannot just look at a fiber cable and assume every optic will work with it. Now let's look at the connectors. One connector you'll see very often in networking is LC. It's a small, compact, and widely used with optical transceivers. For higher density connections, you'll also see connectors such as MPO or MTP. These can carry multiple fibers in a single connector, which is very useful for high density and high bandwidth environments. The connector might look like a small detail, but using the correct connector and polarity is critical for getting the link up. The cable alone isn't enough. We also need a transceiver. You've probably seen names like SFP, SFP+, SFP28, QSFP, QSFP28, QSFP-DD, and others. These modules sit inside the switch or router interface and convert the electrical data from the device into optical signals, or the other way around. But here's something important: just because a transceiver physically fits doesn't mean it's correct. You need to consider things like speed, wavelength, fiber type, distance, and device compatibility. A mismatch here can easily result in a link that stays down. For short distance data center connections, we also have DAC and AOC cables. DAC means direct attached copper. It's commonly used for short, high-speed connections and can be a simple and cost-effective option. AOC means active optical cable. It uses optical technology and can provide more flexibility over longer distances compared with DAC. You'll often see these technologies connecting servers to top-of-rack switches or connecting network devices where the required distance makes sense. So again, the choice depends on the environment, distance, speed, and design. In a real data center, we don't necessarily run every cable directly from device A all the way to device B. That would become very difficult to manage. Instead, structured cabling uses things like patch panels and optical distribution frames or ODFs. Think of an ODF as an organized point where fiber connections are terminated, patched, and distributed. So when you're troubleshooting, the physical path may actually be switch, patch cable, ODF, structured fiber, another ODF, patch cable, remote device. That's why understanding the complete physical path is so important. Good cabling isn't just about getting the link up. It should also be clean, organized, labeled, and maintainable. Imagine troubleshooting hundreds of cables where nothing is labeled. Even if the network itself is designed perfectly, operations become very difficult. Good cabling practices make future changes easier, reduce human error, and dramatically improve troubleshooting. In a production data center, organization is part of reliability. Cable management might look cosmetic, but it's actually operationally important. Cables should be routed properly and supported correctly. We don't want cables hanging everywhere, blocking access to equipment, interfering with airflow, or creating unnecessary stress on connectors. And when someone needs to replace a server, transceiver, or switch, they should be able to identify and access the correct cable without disturbing unrelated connections. Good cable management makes the whole environment easier to operate. Fiber needs some extra care. One important rule is don't bend fiber too tightly. Excessive bending can increase optical loss and potentially damage the cable. Connectors also need to be kept clean. A connector can look perfectly fine to us, but tiny particles of dust or contamination can affect the optical signal. So, when troubleshooting fiber, cleaning and inspecting the connection can sometimes solve a problem that initially looks much more complicated. Now imagine you have a rack with thousands of servers and hundreds of cables. How do you know which cable goes where? That's where labeling becomes critical. A useful label should help identify both ends of the connection. For example, it might tell you the source device and port, destination device and port, or reference information used in your cabling documentation. This becomes extremely valuable during incidents. Instead of guessing which cable belongs to which interface, you can trace the path systematically. Another important consideration is how cables are physically routed. We want organized pathways instead of cables crossing randomly through racks. Good routing helps maintain airflow, reduce physical stress, makes maintenance easier, and keep the installation scalable. Remember, a data center changes over time. Servers are added, equipment is replaced, new connections are installed. If the cabling starts organized, future expansion becomes much easier. Labeling and documentation should work together. The label tells you what you're looking at physically. The documentation tells you how that connection fits into the large infrastructure. For example, if a switch interface goes down, good documentation can help you identify the cable, patch panel, or ODF position, remote device, and remote interface. This can save a huge amount of troubleshooting time, and whenever a connection changes, a documentation should be updated as well. Never assume a cable is working just because it has been installed. Test it. After installation or maintenance, verify the interface status. Check that the expected speed is correct. For fiber, check the optical information when available. Verify TX and RX power levels. Check interface counters. And make sure the correct remote interface is connected. A few minutes of verification can prevent a much bigger problem later. Now we get to one of the most practical parts of this episode, TX and RX troubleshooting. Remember, TX means transmit, RX means receive. If device A is transmitting, that signal must arrive at the receive side of device B. So logically, device A TX connects to device B RX, and device B TX connects back to device A RX. If there's no received signal, start tracing the path. Is the local transceiver transmitting? Is the fiber connected correctly? Is the polarity correct? Is there an ODF or patch panel in between? Is the remote optic installed and working? Thinking in terms of TX and RX gives you a logical way to troubleshooting the physical path. When a fiber link is down, don't immediately start replacing everything. Use a systematic process. First, check the basics. Is the correct interface configured? Is the transceiver detected? Is the remote side active? Then check the physical connection. Reset the optic if appropriate. Inspect the connectors. Clean the fiber. Verify the patching. Then check TX and RX optical power. If one side is transmitting but the other side isn't receiving, that gives you a major clue about where the problem may be. If necessary, isolated components one at a time, transceiver, patch cord, ODF path, structured cabling, and remote side. The goal is to find exactly where the signal stops. So let's bring everything together. Data center networking isn't only about VLANs, routing protocols, VXLAN, or configuration. Underneath all of that is the physical infrastructure. We looked at copper and fiber, single mode and multimode, connectors, optical transceivers, DAC and AOC, patch panels, and ODFs. We also looked at cable management, labeling, documentation, testing, and TX RX troubleshooting. A well-designed network still depends on a reliable physical layer, and when the physical layer is clean, documented, and properly maintained, troubleshooting becomes much easier. And with that, we've reached an important point in the Data Center Fundamentals series. We've completed Season 1 Data Center Basics and Architecture. We started by understanding what a data center actually is, then moved through architectures, Cisco Nexus and NXOS, server deployment models, first hop, redundancy, port channels and VPC, switch virtualization, Nexus routing, and finally data center cabling. So now we have the foundation. and that means we're ready to move forward. In Season 2, Network Virtualization and ACI, we're going beyond the traditional physical network and into modern data center fabrics and network virtualization. So, if you followed Season 1, thank you for being part of the journey. Subscribe to Next Layer Tech, and I'll see you in Season 2.